In this video, I want to take a look at sums of independent random variables. Now to start with here, let's just consider two independent random variables. Let's call these x and y here, and their respective probability distributions, which we can see below here in the form of a table. So we've got the probability distribution for x here, and we also have the probability distribution for y here. Okay. Now, if we sum these random variables and we define this as a new random variable, let's call that z here, we obtain z is equal to x plus y. So z is simply the sum then of our two independent random variables. Okay. And then for z here, we obtain the following probability distribution. So we obtain this table here. So as we can see for z here, we obtain either a 1, a 2, or a 3. And we also have the respective probabilities here. Okay, so that should hopefully be straightforward. Now what we're going to do next here is consider the probability generating functions of each variable. Okay. So hopefully what you obtain here is g of x in terms of t, which is equal to 1 over 4 plus 3 over 4t. We also have g of y in terms of t, which is equal to 1 over 3t plus 2 over 3t squared. And then finally here, the probability generating function of z here. That's our new random variable. So we get g of z in terms of t. And this is equal then to 1 over 12t plus 5 over 12t squared. And then finally plus 1 over 2t cubed. Okay. Now what we're concerned about here, or what we want to ask ourselves, is what happens when we find the product here of g of x in terms of t and g of y in terms of t. Okay. Now don't forget, we defined our new random variable here, z, as the sum of x and y. Now what we're doing here is finding the product then of the probability generating functions of x and y. Okay. And what's about to happen here is really, really important. Okay. So do take a note now of the final line of work in here. So when we do this then, so clearly I just get the product here of these brackets. So this is the probability generating function of x here. So this is g of x in terms of t. This here is g of y in terms of t. So just expanding these brackets here, nice and straightforward, just using FOIL or any method that you're familiar with from GCSE maths, so quite a few years back now. We obtain the following here. So I get 1 over 12t plus 5 over 12t squared plus 1 over 2t cubed. And if you notice here, this is equal then to g of z in terms of t. So that's my probability generating function for z here. So as we said then, what we've just seen here is really, really important. So let's just basically formalize here what we've just found. So let's just summarize here. So if x and y are two independent random variables with probability generating functions g of x in terms of t and g of y in terms of t, then the probability generating function of z here, which is the sum of x and y, is given as follows. So g of z in terms of t is equal then to the product here of g of x in terms of t and g of y in terms of t. So this result here is really, really important. Do make a note of this here. So this result is given in the form of the booklet, so you don't need to memorize it for an exam, and you also don't need to be able to prove this result. So that's always a great thing, right? One less thing for us to be able to prove. Now you should also be aware that if the discrete random variable x here has probability generating function g of x in terms of t, then the probability generating function of y here, which is equal to ax plus b, where a and b are positive integers, this is given as follows. So we get g of y in terms of t here, which is equal to t to the power of b times the probability generating function of x here in terms of t to the power of a. Okay. So this result here is not given in the form of the book, so make sure to memorize this result here. So unfortunately, this one you do just have to memorize, and it will come up on exam style questions. So do take a note of this here. Like I said, very, very important. So that gives us everything that we need here then for our introduction. Let's take a look now at some practice questions here for sums of independent random variables. Let's get started here with question 1. Now for question 1, we are given two independent random variables, x and y here, and we're told they have the following PGFs. So I've got g of x in terms of t, and we also have g of y in terms of t here. And for the first part of this question, it asks us to find the PGF, the probability generating function of the random variable z here, which is equal to x plus y. Okay, so for part A then, where do we begin? Well, if we're looking for the probability generating function of z here, which is equal to the sum of x and y, we need to use the important result here that we established on the previous page. So g of z here in terms of t, that is simply the product then of g of x in terms of t and g of y in terms of t. So g of x in terms of t multiplied by g of y in terms of t, right? So in that case then, for g of z here in terms of t, that will be the product then of g of x in terms of t. So that's 1 over 4 plus 3 over 4t. So 1 over 4 plus 3 over 4t here. And then we have g of y in terms of t. So that's 1 over 4 plus 1 over 2t plus 1 over 4t squared. So if I just write that down here. So 1 over 4 plus 1 over 2t. And then finally 1 over 4 t squared. Okay. So let's find the product here of these brackets. Hopefully nice and straightforward then. So for g of z here in terms of t, what do we get then? Well, I get 1 over 4 times 1 over 4. So that's going to be 1 over 16. So we get 1 over 16 there. We then have 1 over 4 times 1 over 2t. So I get 1 over 8t there. So plus 1 over 8t. We then have 1 over 4 times 1 over 4t squared. So I'm going to get 1 over 16t squared. We then have 3 over 4t times 1 over 4. So I'm going to get 3 over 16t there. So plus 3 over 16t there. We then have 3 over 4t times 1 over 2t. So what I'm going to get here, I'm going to get 3 over 8t squared. So plus 3 over 8t squared. And then finally here, 3 over 4t times 1 over 4t squared. I'm going to get 3 over 16t cubed. So plus 3 over 16t cubed here. Okay. Then all we need to do here is just simplify. So just collect like terms here. And what we find then for the probability generating function of z here in terms of t, so g of z in terms of t. So if you simplify this correctly here, what do we get then? Well, we get 1 over 16. So then I've got the t terms here. So 1 over 8t plus 3 over 16t. So adding those together then we get 5 over 16t. So 5 over 16t there. We then got 1 over 16t squared plus 3 over 8t squared. Add those together here, and what do we get then? Well, I get 7 over 16t squared. And then finally here we've simply got this single t cubed term. So I just get 3 over 16. So 3 over 16 t cubed there. Okay. And there we have it. So nice and straightforward. That gives us the solution there to part A. Now for part B then, as a follow-on here, it says, show that the expectation of z is equal to the expectation of x plus the expectation of y here. So clearly I need three things. I need the expectation of x, the expectation of y, and the expectation of z. So to do that, we need to find g prime of x, g prime of y, and g prime of z, all in terms of t. Okay, so let's just start by doing that then. So to begin with here then, let's find g prime of x. So that's probably the most straightforward here. So g prime of x here in terms of t. So just differentiating our PGF here in terms of t then. Well, 1 over 4 is just a constant, so that will differentiate to 0. And then we've got 3 over 4t here. So when we differentiate that term, we simply get 3 over 4. Okay, so nice and straightforward there. Now for g prime of y here. So g prime of y in terms of t, what do we get here? Well, the 1 over 4 is a constant, so that will differentiate to 0. We then have 1 over 2t, so that will differentiate to 1 over 2. And then finally, 1 over 4t squared, if we differentiate that here, I get 2 over 4t. So 2 over 4 is the same as 1 over 2. I get 1 over 2t there. Okay. And then finally, we need g prime of z here. So g prime of z here in terms of t. So in that case then, this constant here will differentiate to 0. We're going to get 5 over 16. So 5 over 16. We then have 7 over 16, so we times the 7 by 2. So I get 14 over 16, reduce the power by 1. So we get 14 over 16t there. And then finally here, 3 times 3 is 9, so I get 9 over 16 t squared. Okay. So now then, for the expectation of x, the expectation of y, and the expectation of z, we just need to evaluate each of these here at 1. Okay. So for the expectation of x here, that is simply then, so that's going to be g prime of x at 1. So g prime of x at 1, which in this case is simply 3 over 4. Nice and straightforward there. Now for the expectation of y here, so for the expectation of y, what do we get here? Well, again, this is g prime of y here at 1. So if we evaluate this here, then what do we get? Well, I get 1 over 2 plus 1 over 2 times 1, so a half plus a half gives us 1 there. And then finally here, for the expectation of z, again, we just evaluate this here at 1. So that's going to be g prime of z here at 1. So that's going to be 5 over 16. So 5 over 16 plus 14 over 16 plus 9 over 16. Okay, so just evaluate this here using your calculator. And if you do this correctly, then what you should find here is you get 7 over 4. Okay, so we get 7 over 4 there. So clearly, if I can just show then that the expectation of x plus the expectation of y is equal to this value here, then we have done part B. So in that case then, the expectation of x plus the expectation of y, let's do it underneath here. So that's going to be 3 over 4. So 3 over 4 plus the expectation of y, which is 1. So 3 over 4 plus 1 there. So that's the same as 3 over 4 plus 4 over 4, which would give us 7 over 4, which is equal then, that's equal to 7 over 4, which if we notice here, is equal to the expectation of z. Okay, so let's note it here and here. Okay. And there we have it. So hopefully not too challenging there. So that gives us the solution to part B, and that gives us the solution there to question 1. Let's just take a look then at one more question here. So we have question 2 now, and for question 2, we have the random variables x and y here, and they have the following distribution. So both x and y here follow a Poisson distribution, clearly with different parameters. So for x then, our parameter is 3, and for y, our parameter is 1.5. Now for the first part of this question, then part A, nice and straightforward here. It just asks us to write down the probability generating functions for x and y. So let's get started then with part A here. So for part A then, so we need the PGFs here for standard distributions. Clearly the standard distribution here is the Poisson distribution. So we can use our formula book here to help us with part A. So in that case then, if x follows a Poisson distribution with parameter of 3, the PGF here of our random variable x then, so that's g of x in terms of t, that would simply be then e. And normally this would be to the power of lambda times t minus 1. However, in this case, lambda equals 3. So we get e to the power of 3 bracket t minus 1. Nice and straightforward. So that's the PGF there for the random variable x. We then also got y here, so don't forget y. So y also follows a Poisson distribution, this time now with a parameter of 1.5. Okay. So in that case then, again, just applying the standard results here, g of y in terms of t, that is equal then to e to the power of 1.5 bracket t minus 1. Okay, and there we have it. So nice and straightforward. That gives us the solution there to part A. Now for part B then, so for part B here, it says given that x and y are independent, find the PGF for the random variable z, which is equal to x plus y. So to find the PGF here for z, which is equal to x plus y, we need to use the following result here. So g of z then, so that's the PGF for z here, in terms of t, that is equal then to the product of g of x in terms of t and g of y in terms of t. Okay, like so there. So in that case, then what do we get here? Well, g of z in terms of t is equal. So g of x in terms of t here, well, that's e to the power of 3 bracket t minus 1. So we get e to the power of 3 bracket t minus 1 there. And then we times this here by, so we get e to the power of 1.5 bracket t minus 1. Like so here. And then we just simplify this here using the basic rules of indices then. What do we get here? So this is for g of z in terms of t. Well, I'm going to get e to the power of 4.5 then, bracket t minus 1. Okay, so again, hopefully nice and straightforward there. That gives us the solution to part B. So finally then to finish with here, we have part C. Now for part C, then it says using your answers to parts A and B, show that the expectation of z is equal to the expectation of x plus the expectation of y. So again, pretty standard stuff here, right? Nothing too challenging. So in that case, then we need g prime of x in terms of t. We also need g prime of y in terms of t. And we also need here g prime of z. So g prime of z in terms of t. Okay, so we need the following here. So let's start then with g prime of x in terms of t. So just differentiating this here, this PGF, what would we get then? Well, nice and straightforward here. We would simply get 3e to the power of 3 bracket t minus 1 there. Okay, let's keep going here. So for g prime of y in terms of t, well, I'm going to get 1.5e to the power of 1.5 bracket t minus 1. So 1.5e to the power of 1.5 bracket t minus 1 there. Okay, and then finally here, g prime of z in terms of t here, what would that be? Well, that's going to be 4.5 then. So 4.5e to the power of 4.5 bracket t minus 1 there. Okay. And we also clearly need then the expectation of x, the expectation of y, and the expectation of z. And to evaluate each one of those, we need to evaluate each one of these here when t equals 1. So for the expectation of x here, that is going to be g prime of x when t equals 1, which in this case would simply be 3. And why is that the case? Well, if t equals 1, I get a power here of 0 because 1 minus 1 is 0, 3 times 0 is 0, so we get e to the power of 0, which is 1, 3 times 1 gives us 3 there. Okay, so hopefully you can see what's going to happen here then. So for the expectation of y then, nice and straightforward here, we get g prime of y at 1, which in this case would simply give us 1.5. And then finally, for the expectation of z here, what would I get? Well, that's going to be g prime here of z at 1, which in this case will give us 4.5. Okay. Well, basically, we just need to show this here then, which at this point is pretty much trivial now. So in that case then, showing that the expectation of x plus the expectation of y is equal to the expectation of z then. So the expectation of x is 3. So we get 3 here, plus the expectation of y, which is 1.5. So I get 3 plus 1.5. So that gives me 4.5 there, which if we notice here is equal then to the expectation of z as required. Okay, so that's equal to the expectation of z as required. Okay, so That's equal to 4.5, and as required. Okay. And there we have it. So that gives the solution there to the very last question. And that brings us to the end of this video on sums of independent random variables.